Hello everyone, I'm welcoming you all once again to this channel. Today I'm going to make a video on our VASP tutorial series where we will see how to use this hybrid functional like HSC06 use in our VASP calculation. Here I have prepared some input files before and like one I have created with the normal optimization and another with using this HSC06 functional. So first I am going to see this normal one and here I am going to open the INCAR file. So as you can see that this system is only to optimize this Ti to CO2 structure, and here we have taken the precision normal and we don't want to write these files. That's why all these tags are in false. And then ISIF2 we are doing, that is this simple atomic position relaxation without any volume change. Then NELM and NSW we have set for this 220 and 200. Then energy cutoff, force cutoff, and other things we have also given. Now up here we have given that this will perform one van der Waal correction type calculation, and we have used this DFT-D2 method, and that's it. This is a very simple INCAR file for any optimization using our VASP software. Now what changes one has to make when we will go for the HSC type of functional, so that we will see here. Here you check that I'm going to open that HSC, and here I will open that INCAR file. As you can see that all these tags almost same, only this section like this middle section is a kind of difference in between both of these files. And here we have given 4 5 tags which are representing this HSC06 functional. And what are these tags and what are their main thing over here, so that we will see, and how it will define our HSC function, everything we will see, and we will check all these tags one by one using our VASP Wikipedia. So first let me close this normal one, and here I'm going to open it on one side, and here is our VASP Wikipedia. So I'm going to open it, and here you can also do a search over here, that this HSC you can search and you will find some things. And here you see that section of HSC hybrid functional and all, and actually I have visited this section, and this section is more with this density of state and different kinds of calculation what I found. Here as you can see that here it has given n bands and all. So this is the latter part. And first thing is what, so I have found this parameter, one parameter is this LHF calc. So let's search that, and LHF, yes it came. And here you see that it has given that LHC calc specifies whether a Hattie-Fock or DFT hybrid functional type calculation is performed. So there are various hybrid functionals like HSC, PBO, B3LYP and all. So if you want to specify some hybrid calculation, we need to first make it true. So LHF calc should be true for any such hybrid functional calculation. And also if we will make it false, then it will simply calculate for normal GGA or meta GGA. And also it has specified that VASP will default to be PBO hybrid function. So if you will not provide anything, then VASP will calculate this PBO hybrid function. Okay. So also after this tag, you can see that various other tags it has given, like which will help us through the optimization. And here one of them is this algo, which is normal. And also some when you will face some difficulty, you can also use this imix, amix and all. But this LHF calc and this algo is they should be present. And as it is written that In most cases, however, it is recommended to use the damped algorithm with suitable chosen time step. The following setup for the optimization works reliably in most cases. So one can also take the entirely the same thing during any calculation using HSC or any other hybrid functionals. So here our next tag is also algo is equal to damp, so which we have taken from here, and time we have not taken, but if you required you can also take, there is no issue. Okay, so now this part is done. Next is uh, also, yes, another thing here to mention, that as we are mentioning every time about this hybrid DFT, so here you see that hybrid DFT, hybrid functional type calculation and all. So what is the meaning of that? So it is nothing but the mix of Hattie-Fock exchange plus DFT correlation. So this way it can enhance our optimize, it can enhance our structural thing, and it will also provide a better accuracy towards electronic and optical calculation. Okay, so next is AEXX. So let me search that also. So what is this parameter? So this parameter by default will set to 0.25 if LHF calc is equal to true and LRH calc F calc is equal to false. So we have said this LHF calc is equal to true, and also it is a default value, but just to know, I have said this parameter AXS is equal to 0.25, which will specify the fraction of exact exchange in Hattie-Fock type or hybrid functional calculation. Okay, so now what here, uh, another thing here to notice, that we will see, like as we know that our LHF calc is equal to true, but what is this LRHF calc? So I am going to click over here. You see that it shows, it switches on the decomposition of the exchange for the hybrid functional using the full Hattie-Fock exchange at a long range, like this. So if you want any long range type of calculation or anything, then we have to switch on this parameter. But if you don't want, then you can make it false, or you can just leave it because the default value for this is false. So so for our case, this the first condition is satisfying, that's why this AXX value we have taken as 0.25. Okay, this thing is done. Next one is what? HF screen. So here I can see that this is here HF screen. So I am clicking over here. You see that this HF screen default value is 0. So the default value of this HF screen is equal to 0, and here the description given that this HF screen specifies the range separation parameter in range separated hybrid function. So what it does, it is nothing but a screening parameter, and that separates the short range and long range Coulomb potential in a hybrid function. So we need to set some value. So for here, for that you can also go to this examples that use this tag. So here I have opened, you see that this is NIO HSC06, someone has calculated this thing, and here various parameter they have taken, and here you can find one HF screen is equal to zero point 0.2 value they have taken. And although they have commented out this, we can see some other input files. So this one for silicon band structure also someone has done the calculation, and here this HF screen value how much they have taken. So where it is, yes, so yes, here. So here in the hybrid calculation using suitably modified K points, they have used this HF screen is equal to zero point 0.2, and this way we can see some different parameters from some of the example in CAT tags, and that's it. And next one is the pre-fork. Okay, precision of the fork. So here, uh, okay, let's search that tag. So here I am searching Freeze, FOCK. No, we want pre's. Yeah, here it comes. So here it says that this pre's fog, that is the precision for the hattie fog thing, that controls the FFT grades used in the exact exchange routine, and mainly in the hattie fog and hybrid functions. So we can give this to see our simulation whether it will calculate it faster or normal or in single handedly, so you can see all those. Okay, and here are some other descriptions are given over here. You can check that what is the fast meaning and what is the meaning of the normal, and here is one expression, that this E encode how it is related to this G code. So everything we can see from here, and for our purpose I have kept this precision of the fog matrix to be faster. Okay, so with this I am going to like I have tried to simulate this thing, and here what I have found that here I am opening my output file. So here you see that after the one step I have found one error. So the error is suggesting that unsupported exchange correlation functional, please specify the VDWS8 and VDWSR in the INCAR file. As we have taken the van der Waal correction over here using our VDW thing, so for this kind of hybrid functional this is not supporting, so we need to have some extra tags for that. So here let's search that what is this VDWS8 and VDWSR. So I am going to search this. So here is the VDWS8. So what is this? This VDWSA defines a damping function parameter. So like here mainly when we are using some DFT D3 method in the hybrid functional, then we have to specify this VDWSA thing. And what is this VDWSR also we can see, and I'm searching this VDW. Yes, this VDWSR is nothing but it defines a damping function parameter, that is SR. Okay, so based on this we need to, like based on this error thing, and as per this BAS suggestion, what I did, I again did the restart calculation for the same, and here I am opening the INCAR file. You see that here in the INCAR part I have also added two more in car tax. One is this VDWS8, and here the value I have given 1.0 for the damping factor, and this VDWSR here also I have given the value as 0.85. So these are some in like values that others has been used. You can search over here and you will find those values, and I'm not going to elaborate that much. So let's close this. And now the next part here begins with the energy, like the energy comparison. So here I have the output for the HSC, and also for the normal I have the output. Okay, so I will open the outcar file. So I am opening the outcar file here, and here also I am opening the outcar for HSC. Okay, so you see here that, so in the free energy total for a normal calculation, we found the total energy as minus 45.20329274 electron volt, and for this hybrid functional, our energy is now, this free energy total is equal to minus 55.34190088 electron volt. So it means that using our hybrid functional, there are some other terms which are added up, and for that reason we are getting a very highly negative. That means the system is attaining it's even further, it is going, the energy of the system is even going lower. And as we have added some extra terms and all, that means this is highly optimized, and now this is accurately we have optimized the system. So this way you can compare, and some other parameters also you can check. And this video was only about how we can use this HSC06 functional to optimize, or to also we can, here we have started from the very beginning. If you have the webcar or charge car file from your normal calculation, you can simply do the HSC functional from using those webcar and charge car files as well, and it will not take that much time. And this was what I wanted to tell you in today's video. And so thank you all, and bye bye.